Good morning to Ananda. Good morning. So the next topic what we are going to start here is calculation of capacitance of the transmission lines. Calculation of capacitance of transmission lines. Okay, fine. Listen. See, in the similar to the inductance calculation, first of all, if you think about the definition of capacitance, definition of the capacitance, we have to write it as electric flux linkages by voltage. Okay, capacitance we are going to call it as electric flux linkages by voltage. Yeah, so I'm writing that simple definition. Capacitance is equal to electric flux linkages by voltage. Electric flux linkages by voltage. Electric flux linkages sometimes can also be called as charge, net charge. You can say electric flux linkages sometimes as charge. So we can call this C as simply Q by voltage, capacitance as charge by voltage, Q by voltage, or better, you can say this one, even compare it to Q by V, you can write it as dQ by dV. Means rate of change in the electric flux linkage with respect to voltage can be called as charge. So I can say it is dQ by dV. So in the similar terminology, this is the exact formula which we can use all the time. dQ by dV is an exact formula to be used all the time. But this Q by V simply what we have written is valid only in the linear cases. Valid in linear cases. Okay. See, what is the nature of energy stored in the capacitor? Generally, what is the nature of energy stored in the capacitor? Electric energy. You can call it as electric energy. So what is the peak electric energy stored in the capacitor? Means it is half C voltage square, but that voltage we should take it as maximum voltage, or you can say peak voltage. Okay, so peak electric energy stored. Electric energy stored in the capacitor or in the transmission line, also you can say half C Vm square. This will be in terms of joules. Half C Vm square, that will be in terms of joules, you can say joules. Okay, so in the similar lines of inductance calculation, we will be extending our discussion in this way. First, I am going to look at what is the significance of placing the capacitor in the equivalent circuit. Why we have to keep the capacitor in the equivalent circuit? That we'll discuss first. Okay, so after that, we'll take up single phase 2-wire system, capacitance calculation, single phase single wire, and then finally we make certain comments on the 3-phase system. That's it. Okay, yeah, fine. So next we are going to write up significance of capacitance placement in the circuit. Significance of capacitance placement in the circuit. Placement in the circuit means you have to understand that why we are keeping that capacitor in the equivalent circuit. That's the question. Why? Can anybody tell me what's the reason of keeping that capacitor in the equivalent circuit? Transmission line capacitance will be linear only because it is forming in the air gap. So air is a linear dielectric material. So transmission line capacitance is a linear. Transmission line capacitance is linear because it is forming in the air gap. Air is a linear dielectric material. Okay, let's continue. Tell me why we are keeping this capacitance in the equivalent circuit? One, to represent the electric flux linkages. Okay, first one, I'll say C represents the electric flux linkages. Electric flux linkages because of the potential gaps, you can say, because of the potential gap. And second one, this capacitance is going to represent the reactive power delivered by the transmission line. Capacitance is going to represent the reactive power delivered by the transmission line. Okay, C represents the reactive power Q delivered by transmission line, under steady state operation. Steady state operation. Under steady state operation, this is going to represent the amount of reactive power delivered by the transmission line. Okay, next thing. See, I'll tell you. Just listen. It's not to maintain constant voltage and all. Okay, that's not the intention of this capacitor. See, Madhuchandra, don't think in a different way. What you should think is exactly why we are keeping capacitor in the equivalent circuit. Means what property of practical line? He's asking us. He's saying us to keep capacitor in the circuit. That's not purpose of capacitor placement. That's not the purpose of capacitor placement in the circuit. Okay. Next thing. Think here. Earlier we said rate of change of magnetic flux linkage, d psi by dt. What is that name? What is the rate of change of magnetic flux linkage? We know that is current, right? So that is voltage. Rate of change of magnetic flux linkage is a voltage. That's what you have called as induced EMF. But here, what is the rate of change of electric flux linkage? Rate of change of electric flux linkage will be current. That current we are going to name it as charging current. Okay. That current we are going to name it as charging current. So I can say capacitance represents the charging current value. Okay, the charging current formula is nothing but rate of change in the electric flux linkage. dq by dt. That's a charging current. Okay, I will discuss about formula for charging current, reactive power delivered and all at end of the capacitance calculation. Okay, so let's move ahead with some small discussion that how we are going to represent this conductor, maybe power conductor, in the charge distribution form. Okay, listen to this basic word. Very simple word. Stop writing. Listen. If you want to calculate capacitance value, the given conducting system or given conductor system should be taken up in a type of charge distribution. We have to keep that conducting body. Okay. What are the different types of charge distributions we have? You might have studied in electromagnetic theory. Very simple one to recall. Types of charge distributions will be point, line, we have surface, and we will have volume. These are the different types of charge distributions. Like this. Okay, point in the sense you can say coulombs, line, coulomb per meter, surface, coulomb per meter square, volume, coulomb per meter cube. Okay, so these are different types of charge distributions here: point, line, surface, volume. Which is practical among these four numbers? Tell me please. Yeah, that's a synonym. Charge is a synonym for electric flux linkage. Which is practical? Volume. Volume is always practical, not the line, point, surface. Right? Always volume charge is a practical one to be considered. Without a thickness, without a volume, we can't visualize any material. Even though the volume is very less, still volume is existing all the time. So this is practical charge distribution compared to all. This is a practical one. Point is impractical, line is impractical, surface is also impractical. But for the sake of analysis, for the easiness in the analysis, listen to me. For the easiness in the analysis, sometimes this volume is approximated as point. Okay. Sometimes this volume approximated as line. Sometimes it can be approximated as surface. That's the approximation what you are making in your analysis. Considering that volume as point, considering that volume as line, considering that volume as surface. But practical charge distribution will be always volume charge distribution only. Okay. Now, our power conductor, transmission line power conductor, it's having some area of cross section. Listen to me. Area of cross section and a long length. Area of cross section and a long length. Strictly speaking, which charge distribution I should take for line? Strictly speaking, which type of charge distribution I should take for the line? Volume, because it's having some volume, right? Area and then length, volume. But that area is very, very low. Area is very, very low compared to its length. Area is very low compared to its length. So it can be approximated as a line charge distribution. Approximated as line charge distribution. So you have to understood this word clearly. Transmission line conductor approximated as line charge. Approximated as a line charge. Line charge in this analysis. Approximated as a line charge in this analysis. Okay. Now, I will discuss little about that line charge. Then we will move on to the capacitance calculation exactly. Okay. Yeah. So let's move. I am moving to the next slide. For example, we have a line charge here, like this. So line charge. So I am keeping this charge something like plus Q coulomb by meters. Plus Q coulomb by meter. It was a line charge. Line charge. Now I am standing at some point x beside to this x, and this is at a distance of x from the line charge radially. Radially, it's at a distance of x from the line charge. Okay. Now the question is, what is the voltage at this point x? What is the value of voltage at this point x? What is the equation? Equation for voltage at the point x, that we have to know. Voltage. Okay, listen to me, please. Listen to me. Already we know the expression for the field intensity at the x. We know the field intensity at the point x, that is Q by 2 pi epsilon x already. Okay, let me write. Electric field intensity at the point x will be Q by 2 pi epsilon x. That's it. And what is the relationship between this voltage and field intensity? What is the relationship between this voltage and field intensity? You know already E bar equals to minus del V. Already you know E bar equals to minus del V. Okay, so now I'll write Ex equals to minus dVx by dx. Come to be Ex equals to minus dVx by dx. Okay, now you can get this voltage Vx here. Vx equals to minus integral Ex dx minus integral Ex dx. Okay, you substitute that Ex in this equation. So it will come to be Q by 2 pi epsilon x with respect to x. Voltage Vx will come to be minus integral Q by 2 pi epsilon x with respect to x. You take up that integration from this. You can take that Q by 2 pi epsilon out. Ln of, 1 by x will be 1 by x integration. 1 by x integration is ln of x. That minus you have to send inside. So you can get that like ln of 1 by x. Okay. So let me write Vx equals to minus Q by 2 pi epsilon ln of x. So it's approximate expression I am writing. Strictly speaking, there will be some limits here. There will be some limits that we are not considering. But even though you consider those limits, still you end up with this type of expression for the Vx. Vx equals to Q by 2 pi epsilon into natural logarithm of 1 by x. Natural logarithm of 1 by x. Okay. That's the voltage at a point x beside the line charge. That's the voltage at a point x beside the line charge. Okay, so now one small change I want to make here. Small change, that is, let me identify size of this conductor for time being. Size of this conductor, let me identify like this. Yeah, like this we have identified the size of conductor. Radius of this wire is smaller. Radius of that wire is smaller. Now, very simple, very simple. If I move that x, onto the surface of conductor, if I move this x onto the surface of conductor, then what is the voltage on the surface? What is the voltage on the surface? You will get the voltage on the surface, right? If you are moving the point x onto the surface, you will get a voltage on the surface. What you will get now? That x, whatever we have, this we have to replace with smaller. X, whatever we have, this we have to replace with smaller. So ln of 1 by r we are going. So on the conductor surface, so I can give Vr is equals to Q by 2 pi epsilon natural logarithm 1 by r. Q by 2 pi epsilon natural logarithm 1 by r. That's the voltage on the conductor surface. Simple. Next. So why we are thinking about voltage here? Anybody please tell me why you are concentrating on voltage? Anybody? Tell me please. Why you are concentrating on voltage? Nobody is responding. Our aim is to calculate capacitance, na? Our aim is to calculate capacitance. So we will have a formula for capacitance like Q by V. So that's why we are concentrating to calculate the voltage. After getting voltage, we will say simply C is equals to Q by V. Okay, yeah. So let's take up single phase two-wire system. Single phase two-wire system. Capacitance calculation for single phase two-wire system. Single phase two-wire system. This, for example, this is the first line charge I have, forward conductor. It's a second line charge, so called the return conductor. Forward conductor, it is plus Q coulomb per meter. Return conductor minus Q coulomb per meter. Forward conductor A, return conductor B, positive line charge, and then we have a negative line charge. Okay. Distance between these two, we have some value. Distance between these two charges, we have some value. Okay. Listen to. I am standing at some point X here. Between the two line charges, at some point X, whatever it is. That point X where we are standing, is at a distance of dA from the line charge A. And of course, from B, it is at a distance of dB. The point X, what we are concentrating now, is at a distance of dA from the line charge A and then dB from the line charge B. Okay, tell me please, what is the voltage at this point X? Potential, or you can say voltage at this point X. First, I should write due to charge A. Next, I should write due to charge B. And we have to sum up them in order to get the resultant voltage at that point X. Okay, so I'll write voltage at point X. Voltage Vx, I will say Vx. First, due to line charge A, tell me please, due to line charge A, what is the voltage here? Already we have written the equation, right? What is the equation for voltage at any point X here? Q by 2 pi epsilon ln of 1 by X. Q by 2 pi epsilon into ln of 1 by X. Of course, it's a positive charge only, so it's plus Q charge by 2 pi epsilon. Okay. ln of 1 by the distance from that A, charge A is dA, so I should call 1 by dA. I think it's okay for all what I have written. Is it okay for you? What I have written? It's the voltage at point X due to charge A. Next, due to charge B, could you please tell me? Due to charge B plus, it is minus Q by 2 pi epsilon ln of 1 by the distance what we have is dB from the point X to charge B. From the point X to charge B. And you take Q by 2 pi epsilon common from this. Plus Q by 2 pi epsilon, if you take common, natural logarithm 1 by dA minus natural logarithm 1 by dB. Q by 2 pi epsilon, natural logarithm 1 by dA minus natural logarithm 1 by dB. Okay, so this if you simplify, you are going to get like ln of dB by dA. Ln of dB by dA. So I can say voltage at a point X in between the two line charges will be Q by 2 pi epsilon natural logarithm dB by dA. Natural logarithm dB by dA. Okay, done. Okay, one small question. If dB equals to dA, if dB and dA values are equal, where the point X will be? If the dB and dA values are equal, where is the point X we can say? Exactly at middle. I can say that exactly at the center or exactly at midpoint. Okay, let me write. If dB and dA values are equal, dB is equals to dA, then point X is exactly at center or exactly at middle, you can say. dB equals to dA, then point X is exactly at middle. Now, what is the voltage at that point you are experiencing? What is the voltage at that point X you are experiencing? 0. Voltage at that point X will be 0. Voltage at the point X will be 0, and that we are going to name it as neutral plane. Neutral plane. Neutral means 0. Okay. So this we are going to say as isolated neutral plane. Isolated means not connected to ground. Not connected to ground, but still we are experiencing a plane along with we have voltage value as 0. Isolated neutral plane. Isolated neutral plane. So this is the thing. Isolated neutral plane, Vx is equals to 0. Next step. So let's take up the single phase two-wire system now with conductors. Rather than showing a line view, I am going to show the cross-sectional view here. So just check here. So I'm showing two conductors now. It's a forward conductor A, positive charge, and let me show return conductor that's also of same size. I am considering same size we are going to consider. So it's a conductor A plus Q charge, conductor B, and it's of minus Q charge. Radius of this conductor smaller. This conductor radius is also smaller. Distance between these two conductors I will show simply D. Distance between the A and B conductors will be simply D here. Next. Exactly at the midpoint. Exactly at the midpoint, if you stand between the two charges, potential is 0. So I can say voltage at this midpoint will be 0, and this is what we have named already as neutral plane. Isolated neutral plane, where the potential value was 0, where the voltage value was 0. Okay. Because it is operating at negative voltage, Arvind. Other conductor is operating at negative voltage. First one is at plus V voltage. Next one is at minus V voltage. I will prove it. Just listen. Done. Next. See, let's target on our aim. I have to calculate capacitance of phase A conductor and capacitance of the phase B conductor. Forward conductor, return conductor. Okay. For that purpose, try to check what is the voltage on this conductor A. Try to check what is the voltage on the conductor A. See, listen to me. Stop writing. Just listen. Just listen. See, if you want to calculate, voltage at a particular point, wherever it is, voltage at a particular point, that voltage is nothing but summation of all the voltages due to all the charges beside to that. In the vicinity, in the nearhood of that point where you are standing, you might have number of charges, right? And because of all these charges, whatever the voltage will appear at that point, that you should take up as a summation by superposition. So beside to this point A, or this point where we are staying, I have two charges. One is charge A itself, and the next one is a charge B. So I have to take up the voltage at this point due to charge A, and then due to charge B, and we have to sum up them. That's the resultant voltage at the point wherever we have shown on the conductor surface. On the conductor surface A. Okay, tell me please. Because of its own charge, what is the voltage? I'll write the next slide. Conductor A. Conductor A. Voltage. VA is equals to because of its own charge, it will be plus Q by 2 pi epsilon natural logarithm 1 by radius plus Q by 2 pi epsilon natural logarithm 1 by radius. Okay, next thing. Please listen. Because of the charge B, what is the voltage here? Earlier we have written a formula simply like voltage at a point X beside a charge, voltage at a point X beside the charge, Q by 2 pi epsilon ln of 1 by X. Same formula I will use now, but the Q is minus Q now. So it's minus Q by 2 pi epsilon ln of 1 by, what is the distance? I will consider that as D only by saying that radius is very, very less comparatively. You might be getting D plus R or D minus R, D plus R or D minus R. That is neglected, and we are going to take it as simply D, so called the distance between the conductors. So I'll say in the next slide. So because of the conductors are charge V, so minus Q by 2 pi epsilon ln of 1 by D. So if you simplify this one, you will get this like Q by 2 pi epsilon ln of D by R, That is a potential. Oh, class timing, yesterday also I have said, no, class timing is at 6:30. Yesterday also I said, I think class is at 6:30. Yeah, so let's move ahead. Listen to me. So I have found the voltage at this point A. So on the conductor A, voltage. I will ask one very simple question to you. The voltage what you have measured at on the conductor A, listen all of you, stop writing and listen. Voltage what you found on the conductor A surface, with respect to what it is, with respect to what you have taken up that voltage. Tell me, with respect to what you calculated the voltage. Tell me please. With respect to, say, if you want to measure voltage, definitely 2 points should exist, right? It's not definitely with respect to B. It's not definitely with respect to B. At that point, we should take VA minus VB. To get potential gap between them. See, simply if I say voltage at some point is certain value, that we should say with respect to zero potential point. What is the zero potential point now? Neutral is our zero potential point. So whatever the voltage VA we have done now, that is voltage from A to neutral. This point you should remember. Already I said, Sweta, why you are asking same question? Sir, we are calculating at surface. Why have not taken D minus R distance? Already I explained, no, Sweta. R is very, very less compared to small d. So that D minus R or D plus R is approximated to D only. Okay, so let's move. Capacitance. So I'll say capacitance forming from conductor A to neutral. Let's write capacitance from conductor A to neutral. So I'll say it is CAN, capacitance from conductor A to neutral. What is that equation? Charge by voltage. Na? What is charge on this conductor? Plus Q. By voltage is VAN. Okay. So I'll write it is plus Q charge by voltage on this conductor is VAN. And you know already plus Q, VAN formula that you substitute here. VAN formula already we have. So it is plus Q by VAN is this one. Okay. VAN is this one. So, and you simplify this, finally what you can get is 2 pi epsilon by ln of d by r. It will come to be 2 pi epsilon by natural logarithm d by r. That is capacitance from conductor A to neutral. Conductor A to neutral. Yeah, okay, Shweta, okay. See, this epsilon what we have here, that is epsilon not epsilon r. Okay, that epsilon what we have, that is epsilon not into epsilon r. Okay, let's think about the conductor B also quickly. Then we will write capacitance of B and we'll make some comments based on that. Let's continue. Next slide, I'm going to take up. Next slide. So I'll say here conductor B. Conductor B. First, voltage of that conductor B. VB. Voltage of this conductor B, that is VB. First, you try to find out this voltage because of its own charge. Because of its own charge. What is that? Minus Q by 2 pi epsilon ln of 1 by r. Because of its own charge. Minus Q by 2 pi epsilon ln of 1 by r. Okay, because of charge A also I should consider similar calculation. Similar. Because of the charge A also we should consider. So it will come to be plus Q by 2 pi epsilon ln of 1 by d. Ln of 1 by d. Either d plus r or d minus r, it's approximated to d ohm. Now I'll do this modification. Kindly observe, don't confuse. Just look here what I'm saying. Sir, these are analysis for static charges, correct? But conductors having moving charges. See, whether it is a static charge or dynamic charge, all the things will be same analysis, no? It will be of same analysis. That Q value will be continuously changing. The changing value will be cancelled. Ashwin Prasad, you know voltage is proportional to charge, right? Voltage and charges are proportionally same. According to the voltage change, charge also going to be changed by the same value. Okay. Yeah. Let's take up this Q by 2 pi epsilon out. Q by 2 pi epsilon out. And you can have here minus ln of 1 by r. I'll say minus Q by 2 pi epsilon out. Better. Minus Q by 2 pi epsilon I am taking out. So here you will get ln of 1 by r first term. And the next term will come to be minus ln of 1 by d. Minus ln of 1 by d. So it will come minus Q by 2 pi epsilon. And you take this subtraction. By taking the subtraction, you will get this like ln of d by r. This is a voltage at the conductor B. Minus Q by 2 pi epsilon ln of d by r. Obviously, this is that conductor B voltage with respect to neutral reference only. Na? This is that conductor B voltage with respect to neutral reference only. So it is VBN now. I'll show here it's VBN. VBN. How is this VBN compared with VAN? How is this VBN value compared with VAN? One and opposite. Just observe. So this conductor B2 neutral voltage, conductor B2 neutral voltage is equals to negative value of conductor A2 neutral voltage. conductor B2 neutral voltage is equals to negative of the conductor A2 neutral voltage. Now let's take capacitance from B2 neutral. Capacitance from B2 neutral. Obviously, applied voltage only this. It's applied voltage to the conductors. What we say. See, actually, what you are applying to the conductors is it charge or voltage? Voltage you are applying that you know. Based on that, the charge is getting created. How much charge is getting created? That depends upon the dimensions. That's the point of talk here, exactly speaking. Okay, so how much voltage you are applying, based on that one, the charge is getting created. And how much charge is getting created means it depends upon the dimensions and material of the body what you are taking. Yeah, so let's see. Conductor B2 neutral capacitance here, CBN, this one. Conductor B2 neutral capacitance. Capacitance from B2 neutral. So it is CBN. It is simply charge of the conductor B is minus Q. Charge of the conductor B, that is minus Q, by potential VBN. By the potential is VBN. And you can write it minus Q by. Already VBN is minus VAN. Already VBN value was minus VAN, just now I said. So minus minus is cancelled out. So you will get it is Q by VAN. And this is nothing but capacitance from A to neutral. Capacitance from A to neutral. So finally, capacitance from B to neutral and capacitance from A to neutral are equal. Equal to what? Equal to 2 pi epsilon by ln of d by r. That epsilon is nothing but epsilon naught into epsilon r. So you'll get this like 2 pi epsilon naught epsilon r by natural logarithm d by small r. D by small r. Okay, so capacitance from conductor B to neutral and conductor A to neutral, 2 by epsilon naught epsilon r by ln of d by r. Just think about this one. Listen all of you. What is epsilon naught value? Epsilon naught 8.854 into 10 power minus 12 farad by meter. Epsilon naught number is 8.854 into 10 power minus 12 farad by meter. Okay, what is epsilon r? Relative permittivity of the surrounding medium. Relative permittivity of the surrounding medium. As it is air, epsilon r is equals to 1, we will substitute. Epsilon r value will substitute as 1 because the surrounding medium is air. ln of d by r, it's a constant number. So units will be only for epsilon naught in the whole equation. Units will exist only for this epsilon naught. That units are farad per meter what we are going to consider. So capacitance from A to neutral and B to neutral are same. That will be coming in farad per meter, in the sense for 1 meter length of conductor. For 1 meter length of conductor, this is the capacitance value what we can experience. And if length is increasing, according to that, capacitance value also going to be increased. Yeah. So next, let me take up the capacitance between the two conductors. Capacitance existing between the two conductors. I'll take up that. So let me repeat this diagram. This one I am repeating, same diagram. Just see the modifications, how I am making this one. Just check this one. So I'm clearing this. Okay. So I want to find out capacitance between these two conductors now. What is the capacitance between these two conductors? So called CAB. capacitance between the two conductors. I want to take up that as CAV. CAV. Epsilon R no units. Epsilon R will not have any units. It's a relative number. Okay. See, capacitance between the two conductors CAV, A and B, CAV. Just could you please tell me? How this CAN CBN are connected? How that CAN CBN are connected? Yeah, tell me please. How that CAN CBN are connected? Series. So it will be the series combination of capacitances AN and BN. Series combination of CAN and CBN. Okay, so if you want to take up that series combination, I can say 1 by CAB is equal to 1 by CAN plus 1 by CBN. 1 by CAN plus 1 by CBN. How are these two numbers, CAN and CBN? How are these two numbers, CAN and CBN? Equal? Already we said in the previous slide, right? CAN, CBN values are equal. So as we know, this capacitance from A to neutral and capacitance from B to neutral are equal. You can write 1 by CAB value like 2 by CAN. 1 by CAB value is equals to 2 by CAN. And you can write CAB value 1 by 2 times of CAN. 1 by 2 times of CAN, you can say. Yeah, so let's move in the next slide. So capacitance from A to B is nothing but CAN by 2. CAN by 2. What is that CAN by 2? CAN 2 pi epsilon naught epsilon R by ln of d by r. This by 2. This by 2 means you'll get this like pi epsilon naught epsilon R by natural logarithm d by r. This will be in farad by meters. Capacitance between the two conductors CAB is equals to pi epsilon naught epsilon R by ln of d by r in terms of farad per meters. Okay. Moreover, it is a conductor to conductor capacitance only for single phase two wire system. This is only for single phase two wire system. Single phase two wire system. Only for the single phase two wire system. Okay. So now let's take up one more small calculation here. One more small calculation I want to take up in the next slide. Okay. A voltage between the conductors A and B. Voltage between A and B conductors. A and B conductors. Just take this now. See, you have voltages like VAN and VBN here. You have voltages like VAN and VBN. What is voltage between the two conductors? I can say. What is the voltage between these two conductors? I can say it is VAB. That is nothing but VAN minus VBN. VAN minus VBN. So VAB is equal to conductor A2 neutral capacitance minus conductor B2 neutral capacitance. VAN minus VBN. VAN minus VBN. See, already we know this VBN value as negative of VAN. We have done this already, right? VBN value nothing but negative of VAN. So you can get here VAN minus of minus VAN. So it will come to be 2 times of A2 neutral voltage. 2 times of A2 neutral voltage. And A2 neutral voltage, if you write, it will be like VAB by 2. A2 neutral voltage, it will come to be VAB by 2. And what will happen to B2 neutral voltage? B2 neutral voltage, negative of VAN, so it will be minus VAB by 2. B2 neutral voltage, it will come to be minus VAB by, like this you can say. Conductor A2 neutral voltage is VAB by 2, conductor B2 neutral voltage is minus VAB by 2. Okay, so let's say in the next slide. So, for example, if you have two conductors with some conductor to conductor voltage, for example, we have two conductors here. It's a conductor A and it's a conductor B. Just observe my words, what I am saying. Conductor A, conductor B. And voltage between these two conductors, I am saying something like 400 volts. Voltage between the two conductors, I am saying as 400 volts. 400 volts. What is the conductor A voltage? And what is the conductor B voltage? Anybody please tell me. What is conductor A and conductor B voltage? Conductor A plus 200, conductor B minus 200. Yes or no? So first one is half of this value positive, and second one is half of this value negative, like this. So conductor A voltage is plus 200 volts, conductor B voltage is minus 200 volts, you can say. Plus 200 and minus 200. In case of three phase, we are not discussing now, Vishnu. We are saying about only single phase system. See, do you have that single phase two-wire system practically? Do you have the single phase two-wire system practically? Yes or no? Do we have the single phase two-wire system practically? Yes, we have it in the what we call secondary distribution system. Secondary distribution system. For example, if you think about the practical single phase two-wire system, single phase two-wire system. So I have two conductors here. One you say phase in that, and other wire we are going to call it as neutral. Yes or no? One wire you say as a phase wire, next wire we say it as neutral. Whether this neutral is grounded or not. Whether this neutral wire, what we are getting for our house, neutral wire, what we are getting for our house, is it grounded or not? Yes, definitely. Where? In case of distribution transformer. At the location of the distribution transformer, it is grounded. Grounded. See, once if it is grounded, what is the voltage of that neutral point? Once if it is grounded, what is the voltage of that neutral point? Definitely 0. This value will be 0. Because it is grounded, ground potential we are taking as 0. So neutral voltage also becomes 0. Now you tell me, in case of this practical system, if I have a voltage applied of 250 volts between them, between the two wires, if I have a voltage of 250, what is the phase conductor voltage and what is the neutral conductor voltage? What is the phase conductor voltage and what's the neutral conductor voltage? Phase conductor will directly operate at 250. Neutral conductor operates at 0. 250 and 0. See, listen. It's a practical system. Practical single phase two-wire system. But the system what we are discussing now, it's a single phase two-wire, but no one of these two conductors are connected to ground. No one of these two conductors are connected to ground. That type of system we are discussing here. Okay. So single phase two-wire, and no one of the conductor connected to ground. No one of the conductor is connected to ground. Okay. Just to say that difference only I am discussing about this one, nothing more than that. Okay. So anyhow, from this point onwards, I am going to extend with a single phase two wire system, no one of the conductor connected to ground only. This system only I am going to extend further and further, not the second one, not the second one. Capacitance formula will be same. Even though the other conductor was grounded, for example, if you want to say conductor from phase to neutral here, conductor between phase and neutral wires, between phase and neutral wires will be pi epsilon naught epsilon r by natural logarithm distance between the two conductors by radius of the conductors. Okay, you call this distance as small d and radius of each wire as small r. Then it will come to be pi epsilon naught epsilon r by ln of d by r farad by meter. Formula will be same. Only one capacitance. Only one capacitance. Okay, let's move. Let's move in this manner from this point. Listen, please. Listen, all of you. See, in this single phase two wire capacitance calculation, single phase two wire system capacitance calculation, we have taken only two conductors. Only two conductors we have taken. And we have seen the effect of one on the other in the voltage calculation and capacitance calculation. But if there is another conductor beside to this, tell me, listen. If there is another conductor beside to this, then definitely that conductor also shows some effect on these capacitance values and voltage values. Will you believe it or not? Let's look at my question, what I am asking you. I am discussing about only two wires. The effect of one on the another I have taken up in the voltage calculation and capacitance calculation. But if there is a third wire, definitely the effect of the third wire must be taken up in the calculation of the voltage and the capacitances. Okay, now see this. Now, practically speaking, we are keeping these conductors at a finite height from the ground. At certain height, maybe 5 meters from ground level, 4 meters from ground level. Like that, we are keeping the conductors. Conductors we are keeping at a finite height from the ground. So ground is a conductor, as you know. Definitely, we will be having effect of ground in the voltage as well as a capacitance calculation of the conductors. Yes or no? Yes or no? Definitely, there will be an effect of ground on the capacitance calculation. So, with effect of ground, how is the capacitance calculation and how is the capacitance value that we are going to extend further? Okay, so our next heading is effect of earth in capacitance calculation. Single phase two wire system only, in bracket. Single phase two wire system with no conductor connected to ground. No conductor connected to ground. No conductor connected to ground. Single phase two wire system with no conductor connected to ground. Listen now. So I am taking a single phase two wire system first. It's a conductor A, and beside to that we have conductor B. Conductor B like this. So it's A and B. A is of plus Q charge, B is of minus Q charge, radius of A, and this is radius of B. distance between AB conductors, I am showing it is D. Distance between AB conductors, I am showing as D. And we are keeping these charges above the ground at certain level. Let me show that level. It is that ground level I am showing. Okay. Yeah. So it's a ground or earth plane, you can say. Ground or earth plane. Next thing. Next thing, listen. A very simple discussion. Don't confuse. Don't confuse. I will ask some questions in a sequence. Just answer these things. Answer these things. Exactly at midpoint, I am locating one point here. Exactly at middle, I am locating one point. What is voltage here? What is voltage at this point? 0. Because both plus Q and minus Q charges are at equal distance, potential will be 0. Yeah. Next thing. Listen. Next thing. What is voltage at this point? Voltage at this point. See, actually, to know whether the voltage is 0 or non-zero, we should check whether the point where you are taking, is it equal distance from plus Q and minus Q. If it is at equal distance from plus Q and minus Q, then potential will be 0. Obviously, this point is at equal distances from plus Q minus Q, voltage is 0. And what is the voltage here? Also 0. What is the voltage here? Also 0. Not only that, along this line, anywhere you take, potential will be 0. Potential will be 0. Okay, next thing. Next thing. Very simple question. Is it 0 or non-zero? That's our question here. That's our requirement. Tell me, what is the voltage here? What is voltage at this place? Because of these two charges. Because of these two charges. 0 or non-zero? Non-zero. Non-zero. Okay. Some value we have here V1. Some value we have V1. What is voltage at this place? Is it 0 or non-zero? Is it 0 or non-zero? Non-zero. That's also non-zero. And let's say this is V2, some value. And what is the voltage at this point? Non-zero. That's the value I'll say V2. My question is, we have voltages like V1, V2, V3, whether these values are 0 or non-zero. Sorry, whether these values are equal or unequal. V1, V2, V3 we have, whether these values are equal or unequal. Definitely unequal. Definitely these values will be unequal. Okay, now next, listen. For example, if I take one conducting body, assume that this is a conducting body. Ground is treated as a common reference plane or a conducting body, basically speaking. Just listen to me. So it is a conducting body to me. It's a conducting body. If I apply some voltage V to this, if I apply some voltage V to this one, then if I measure voltage at any point on the surface, at any point, if I measure that voltage, it will be remain same. All of you understood my point, what I'm saying? If I apply some voltage to a conducting body, then obviously voltage at all the places on that conducting body will be equal. That is one of the very basic statement of electromagnetic theory. Now the question is, this ground or earth is treated as ideal conducting plane. Ideal conducting plane. See, if it's an ideal conducting plane, the property of this ideal conducting plane will be voltage at all the places must be equal. Voltage at all the places must be equal. But these voltages are becoming unequal. That's the issue what we are facing now. So we are not satisfying the ideal conducting plane properties here. Ideal conducting plane properties. See, actually, listen. You might have this type of confusion. I want to clear it. Just listen. Theoretically, on the paper, we have taken two charges and we have taken ground, and I am calculating voltage on this ground plane. Voltages are coming unequal. Voltages are coming unequal. But practically speaking, voltages are equal. Na? Practically speaking, voltages are equal on the surface of ground at all the places. Which is correct? Practical one or theoretical one we are doing on paper? Which is a correct statement? Practically, voltage at all the places on the ground is same because of the ideal conducting plane properties. Okay, but because of this theoretical study, I am saying voltages are unequal. Which statement is correct? Practical one or theoretical one? Practical one is always correct. Practical one will be always correct. Now we have to modify. Listen to my words, please. We have to modify our theoretical study. Our theoretical study, what we are doing on the paper, such that it should satisfy the practical properties. It should satisfy the practical properties. For that purpose, I will be keeping some charges below the ground on the paper, not in the ground by digging the ground. On the paper, we are keeping some charges inside the ground or below the ground level in order to maintain the properties of the ideal conducting plane. Okay. So for example, if this conductor A is at a height of h from the ground, let me assume B also at a same height from ground. I am keeping some charge below the ground here at a depth of h. At a depth of h, I'll call this charge as A dash, but I'll say it is negative of the above one. Above one is positive, bottom one, which we are drawing, that is negative. I'll show one more charge, that is a B charge, B dash, to say this one, and it's a plus Q because B is positive, sorry, minus Q, so B dash will come plus Q, and this depth is h. Depth is h. This distance is d now. This distance is d. Okay. So let me write this statement. Very simple. Whether these charges A dash and B dash, what we are drawing on paper, whether these are physically existing or not, whether this A dash and B dash are physically existing or not. No. So these are going to be called as imaginary charges or image charges. These are called as image charges. Okay. Now tell me whether this A and B above the ground, what you see, A and B, whether these are physically existing, whether this A and B are physically existing or not. Yes, these are physically existing. So you can call these charges as physical charges. Physical charges. So this study we are going to call generally theory of images or Kelvin's images law. Okay, so I'll write that. Theory of images or Kelvin's images law. Theory of images, or you can call it as Kelvin's images law. Okay, I'll show the next slide. Just listen to me. Tell me now. Very simple question. What is voltage at this point now? What is voltage at this point? Zero or non-zero? Distances you should check. Plus Q minus Q equal distance, cancelled out. Minus Q plus Q equal distance, cancelled out. V1 will be 0. What is V2? Plus Q minus Q equal distance, cancel. Minus Q plus Q equal distance, cancel. 0. What is V3? Also 0. So at all the places, the potential is equal. Equipotential. Following. So by that way, we satisfy the properties of the ideal conducting plane, you can see. Okay. So let's say in the next slide, the theory of images I am writing, right? To satisfy the properties of ideal conducting plane, ideal conducting plane in bracket ground, ideal conducting plane in bracket ground for each physical charge, existing above the ground, existing above the ground, there should exist an image charge below the ground. There should exist image charge below the ground. Okay, so this we can say as theory of images, or you can say Kelvin's images law. And image charge should be exactly opposite of physical charge. Okay, and depth, for example, physical charge is at a height of 9 meter. Image charge also should be at a depth of 9 meters. Okay, height and depth must be equal. Yeah, done. So see, we have to calculate capacitance of conductor A to neutral. Let us say effective capacitance of conductor A. Effective capacitance of the conductor A we have to calculate. So for that purpose, simply now we should consider the effect of B. Already we are taking the effect of B. Not only that, we should take the effect of A dash and we should take the effect of the B dash also. After taking this A dash and B dash effects in the capacitance calculation of A, that capacitance I will say as capacitance from conductor A to neutral, including the earth effect. Capacitance from conductor A to neutral, including the earth effect. Okay, yeah. So I'll say in the next slide. Just formula I'm going to give. I'm not going for any derivation of capacitance from A to neutral, including earth effect. With earth effect. Capacitance from A to neutral. Just follow the formula. Listen to my words, please. All of you stop writing. We have already derived expression for capacitance, right? Expression for capacitance. That is 2 pi epsilon naught epsilon r by ln of d by r. Remember always. If you want to find out capacitance per phase, or capacitance from one conductor to neutral, it will always start with 2 pi epsilon naught epsilon r in the numerator. Always it will start with 2 pi epsilon naught epsilon r in the numerator. Okay. So I'll say here with earth effect 2 pi epsilon naught epsilon r by, check this one, by natural logarithm. Look here, natural logarithm d by r into natural logarithm d by r into, just look this one, it will be coming like 2h by square root of 2h square plus d square. This will be in terms of Faraday diameter. 2 pi epsilon naught epsilon r by ln of d by r into 2h by root of 2h square plus d square. Like this you can get by including the earth effect. Earlier we derived capacitance from A to neutral without earth effect, right? Without earth effect, earlier we have derived. Let me write that equation also here. Without earth effect. Without earth effect, capacitance from A to neutral will be 2 pi epsilon naught epsilon r by natural logarithm d by r. This is another formula what we have written in the previous case. Two pi epsilon naught epsilon r by ln of d by r. And you tell me, by looking at these two equations, when it is preferable to neglect the arithmetic? When we can neglect the arithmetic? Anybody? When it is preferable to neglect the arithmetic? If d is less, h is very, very high compared to d. Height is more, 2h equals to d, h is much more than. Okay, listen to me. I'll give some numbers of d and h. You are about to compare d and h, na? I'll give some numbers of d and h. Could you please tell me, is it possible to neglect the effect or not with that? Okay, let's say, for example, distance between the conductors is 3 meters. Height of the conductor from ground, level, h, 5 meters. Tell me please, is it possible to neglect the earth effect or not in these numbers? With these numbers, is it possible to neglect the earth effect or not? D value 3 meters, h value 5 meters. Okay, let's do little calculation. What is 2h value? 10. 2h value 10. What is 2h square plus d square? 2h square means 10 square. D square means it is 3 square. 2h square means 10 square. D square means 3 square. You take under root of this. So it is 109 under root. Huh? So 100 plus 9, it will be 109 under root. Tell me please, what is this number? Root 109. How much it will come? It will be 10.44. 10.44. Okay. So I was interested to calculate this value 2h by root of 2h square plus d square. How much is this now? 2h value 10 by this value 10.44. And this 10 by 10.44 will give you 0.9578 or 958. You will get that number like 0.958. 0.958. Okay. So what value we have calculated here? What value we have calculated means, just if you look back to the equations. See, from these two equations, if you observe, from these two equations, only the term which is differing from 1 to 2 is this. The term which is differing from equation 1 to 2 is 2h by root of 2h square plus d square. Only this term is differing from one to the other. Okay, now the thing is, listen please. This value what we calculated is coming 0.958, means close to 1. That number is coming very, very close to 1. Yeah. Yes. So if this number is very close to 1, both equations will give same final value, right? Both equations will give same answer. Yes or no? Yes or no? Is it possible to neglect the earth effect with the calculations what we have done or not? Is it possible to neglect the earth effect with the calculations what we have done? Yes, we can neglect the earth effect. Okay. So what is the conclusion we have to make from this is simply, we should not compare the values of D and H directly. Whether to neglect the earth effect or consider the earth effect, we should not compare the values of D and H directly. If you compare these two, you can't say whether the earth effect can be neglected or not. Whenever this ratio, listen to me, whenever this ratio is coming very close to 1, then only earth effect can be neglected. When this ratio will come very close to 1, whenever this d square value is very, very less, compare it to 2h whole square. D square value was very, very less compared to 2h whole square. At that time, the summation will be close to 2h whole square only. Square root will give 2h, 2h will be cancelled. So I can say, earth effect can be neglected. Earth effect can be neglected only when D square is very, very less compared to 2h whole square. D square is very, very less compared to 2h whole square. In that case only, earth effect can be neglected. Is it practical? Is it practical? Just visualize practical transmission lines, what you have seen outside. Just visualize the practical transmission lines, what you have seen outside. Is it practical or not? Yes, many times. Many times it will be practical, right? Just if you look at the practical lines outside and how is the height of the conductor from ground and how is the distance between the conductors. D is a bit small comparing height. And if you take up the D square and 2h whole square comparison, D square will come very, very less compared to 2h whole square. Means I'm going to say it is very practical for overhead lines. It's very practical for overhead lines. That's why if you are going for capacitance calculation of overhead lines, you can neglect the earth effect. You can neglect the earth effect, right? So this is very practical for overhead lines. So most of the times, if you are going for capacitance calculation of overhead lines, this earth effect can be neglected, but cables we can't neglect. Okay. But a tower H value will be quite low. Where you have seen Vijay? Quite low is how much? 1 meter, 2 meters? Vijay. Yeah. So let's continue. I'll say I want to have a comparison between these two. Okay, almost same. That's okay. Almost same, but still, among these two numbers, which number looks to be more? Among these two numbers, which number looks to be more? Yeah, even you consider the insulated string length and all, minimum ground clearance has to be maintained, no, Vijay? Minimum ground clearance has to be maintained. Always the ground clearance is measured from conductor to ground, not between tower and ground, not between the cross arm and ground. We have to measure the clearance from conductor to ground. Okay. Yeah, which capacitance is more among these two means with earth effect capacitance will be more, because this number 2h by root of 2h square plus d square will be definitely less than 1. Definitely less than 1. Less than 1 into d by r will be less than d by r. Denominator value little less compared to below equation. So obviously capacitance with earth effect will be little more, maybe 2% more or 3% more, like that we can expect. Okay, so I can say CAN with earth effect will be greater compared to without earth effect. CAN with earth effect greater compared to CAN without earth effect. Yes. Next thing. So next, let me take up a single phase, single wire system quickly. Capacitance. Single phase, single wire system. So we have only one conductor above the ground. It's a plus Q conductor, you say, and we have ground surface now. We have ground surface, something like this, or earth, ground or earth. And this conductor A, what we have taken now, is having a radius smaller. This is at a height h from the ground. This is at a height h from the ground. Tell me please. Tell me please. What is capacitance of this conductor A to neutral? What is the capacitance of conductor A to neutral? That's the question. Capacitance of conductor A to neutral. All of you listen to me. With what term I should start the numerator? Capacitance of A to neutral means with what term I have to start the numerator? 2 pi or pi? 2 pi. 2 pi. 2 pi. 2 pi epsilon naught epsilon r. Okay. So I should say 2 pi epsilon naught epsilon r by general formula we used to say in the denominator ln of d by r. Ln of d by r. Ln of d by r means what is d? What is a d? That's the distance between the forward conductor and return conductor. Distance between the forward conductor and return conductor. Already we have taken forward conductor. Where will be the return conductor? So if you have only one conductor like this in capacitance calculation, definitely we should take the image conductor. Image conductor, then only we should consider the capacitance calculations. Okay. So I'm showing that image charge below the ground. It is A dash, I can say, and it's minus Q. And again, this is also at a depth of h. That's also at a depth of h. Okay. So I can say this like 2h by r. Calling this like 2h by r. This will be in farad by meter. 2h by r. Distance is how much? 2h. 2h by radius. 2h by radius. Okay. So it's about single phase, single wire. Next, we'll think about single phase, three phase system. 3 phase, 3 wire, you can say. 3 phase, 3 wire. Yeah. So very simple, very simple. Above the ground, if there is only one charge existing, only one conductor existing, definitely we should take the image charge and then only we have to go for the capacitance calculation. Okay. Yeah. So let's see 3 phase system. 3 phase system. Capacitance calculation for the 3 phase system. So I'm showing 3 wires here, phase A, phase B, phase C. This is phase A and phase B, and here we have phase C. Right. Phase A, phase B, phase C. 3 phases. Voltages, I will tell you. Voltages. First one, V phase at an angle 0 degree. Second one, V phase at an angle minus 120. Third one, V phase at an angle plus 120. Positive sequence. We said already, positive sequence. Say, in similar to these voltages, charges will be taken up with the same angles. First charge, Q at an angle 0. Second charge, Q at an angle minus 120 degree. Third charge, Q at an angle plus 120. Charge and voltage proportional always. Charge and voltage are proportional always. Okay, next thing. Ground effect is neglected. In these calculations, ground effect is neglected. Already we discussed in the starting of this chapter. We said that we have some capacitance existing between A and B conductors. B and C, and then C and A. So I'm showing that capacitance here. A to B, B to C, and then we have from C to A. AB, BC, and this is CA. These are called as interline capacitances, or you can say line to line capacitances. These are interline capacitances. Line to line capacitances, you can call CAB, CBC, CCA. Tell me how these three are connected? How these three are connected? A to B, B to C, C to A, na? How these three are connected? Delta. These three are connected in delta. But we need capacitance per phase to be kept in the equivalent circuit. We need the capacitance per phase to be kept in the equivalent circuit. Stray capacitance are neglected. Ground effect is neglected. Listen to me. So to get the per phase capacitance, this delta connection, we have to convert into star. Delta connected interline capacitances. Now we are going to convert these things into star. Like this, you can say. Is A2 neutral, B2 neutral, and then this is C2 neutral. It's a neutral. It's point A, point B, point C. A2 neutral, B2 neutral, and then this is C2 neutral. Star. Yeah. Next thing. Next. How will be these three capacitances to be expected? Whether these are equal or unequal? Let's say equal. Let's say equal. In the next slide, I will write. Next slide, I am writing. Just listen. Capacitances from conductor A2 neutral, conductor B2 neutral, conductor C2 neutral, all are equal. That is nothing but capacitance per phase. That is nothing but capacitance per phase. Capacitance per phase. What is the equation? How we have to write this equation? Starting with 2 pi or pi? Starting with 2 pi or pi? It will be starting with 2 pi. It will be starting with 2 pi. So numerator will be 2 pi epsilon naught epsilon r. Numerator will be 2 pi epsilon naught epsilon r by natural logarithm. See, we have written earlier d by r. We have written earlier it is d by r, but now I will say it is GMD by radius of the conductors. GMD by radius of the conductors. Not GMR. GMR will not come. Na? GMR will not come in this capacitance calculation. We'll get only size or radius of the conductors. So it's 2 pi epsilon naught epsilon r by ln of GMD by r, farad by meter. Okay, and what is this GMD? The GMD is equal to cube root AB distance, BC distance, and then CA distance. A to B, B to C, and then C to A. Could you please tell me? When this whole box is valid? When this is valid? Tell me please. When this is valid? This is valid either for symmetrical configuration system or unsymmetrical transposed one. Symmetrical configuration system, or you can say unsymmetrical transposed system. So valid for symmetrical or unsymmetrical transposed system. Unsymmetrical transposed system. Transposed configuration. Right? Symmetrical or unsymmetrical transposed configuration operating for balanced voltages. Okay. Operating for balanced voltages. Earlier we have written operating for balanced currents. Now we have to say operating at balanced voltages. Balanced voltages. Done. But if it is a bundle conduct system, in place of R, we keep DS. Bundle. Bundle conduct system, we keep DS in place of R. And there you can see that 0.7788 has to be removed from the GMR calculation. DS calculation will be similar to GMR, but only that 0.7788 will be missing in that. Okay. Yeah. Next. Then this equation can't be used. Amrit. For example, voltages are unbalanced. Voltages are unbalanced. Symmetrical configuration means equilateral spacing. Then even this equation we can't apply to find out the capacitances. Yeah, so let's have a break of 5 minutes. 5 minutes break, only 5 minutes, 5 minutes. After that break, I will discuss some conclusions regarding this capacitance calculations. 5 minutes break. I have resumed the audio, video, and screen. Yeah. So let's continue. Yeah, I'm not discussing any derivation here, Pramod, regarding the GMD. Okay. Just I have given the final equation with the extension. Yeah. So let's move. Let's move ahead with the conclusions with respect to capacitance calculation. Conclusions on the capacitance calculation. First one. Already you know that this capacitance is a shunt element. Already you know that this capacitance is a shunt element, and that shunt capacitive reactance formula we are going to write. Shunt capacitive reactance formula, or you can say sometimes as line charging reactance, any name. So shunt capacitive reactance per phase, shunt capacitive reactance per phase, or line charging reactance per phase. Line charging reactance per phase. So I'll say it is XC per phase here, XC per phase. See, formula for this shunt capacitive reactance is 1 by 2 pi of C per phase. 1 by 2 pi of C per phase. 1 by 2 pi of C per phase. Okay, next. So units of this one will be obviously ohms. Units of this shunt capacitive reactance is ohms. And this capacitance value we are substituting in farad by kilometer. Keeping this capacitance in terms of farad by kilometers. Farad by kilometer. Then what's the overall units of this one? What's the overall units of this one? 1 by kilometer. 1 by kilometer means it will come to be ohm kilometer. It will be coming like ohm kilometers. 1 by kilometer. So it will be coming like ohm kilometers. That is the shunt capacitive reactance per phase. Next one. What is the expression for the charging current per phase? Charging current. Just look here. See, this is the three-phase system we have now. And what is the rated voltage of this conductor? Phase voltage. This conductor voltage is V phase. And neutral voltage is already we said 0. Already we said the neutral voltage 0, and this point voltage is V phase. And current flow in this we can call as IC per phase. Current flow in this one we can say as charging current per phase, which is nothing but V phase by XC per phase. V phase minus 0 by XC per phase. So I can say charging current per phase, charging current per phase, IC per phase will come to be phase voltage by capacitive reactance per phase. Phase voltage by capacitive reactance per phase. And this will come to be V phase by XC per phase, in the sense it will come to be 2 pi F into C per phase here. V phase into 2 pi F into C per phase. 2 pi F into C per phase. And from this, you will come to know that this capacitance is, this charging current is proportional to voltage, frequency, capacitance. Voltage into frequency into capacitance. Charging current will be proportional to voltage into frequency into capacitance. Voltage, frequency, capacitance. Okay, done. Next thing. See, can I say line charging current and per phase charging current both are equal? Can I say that line charging current and per phase charging current both are equal? Sir, no. Yes, of course. Just if you look this diagram, this is charging current per phase, and the same current will be carried by the line also, right? Same current will be carried by the line also. So line charging current, per phase charging current, both will be exactly equal. There is no difference in the two values. Okay. So in the examination, whether he is asking per phase charging current of transmission line wire or line charging current, both will be equal. Line charging current, both will be equal. Okay. So let's move to next term here, to the next term, that is reactive power delivered by the transmission line. Q delivered by the transmission line. Next one. Q delivered by transmission line. Reactive power delivered by the transmission line per phase. I'm going to say it as per phase. I'm going to say it as per phase first. So I can say it is QC per phase here. QC per phase. Yeah, could you please tell me, is it a shunt element or series element we have? Is it a shunt element or series element? Yeah. Shunt element or series element? It will be shunt element. Shunt element in the sense we have to say this one in the manner of voltage. So I can say here phase voltage square by XC per phase. Phase voltage square by XC per phase. If you want to consider this three-phase number, you should multiply this with 3. So 3 into phase voltage square by XC. And you can write it as 3 into phase voltage square. 1 by XC per phase will come to be 2 pi F into C per phase. 1 by XC per phase will come to be 2 pi F into C per phase. Phase voltage square into 2 pi F C per phase multiplied with 3. And from this, you know, QC proportional to voltage square, frequency, capacitance. Voltage square, frequency, capacitance. This is the reactive power delivered by the transmission line. Reactive power delivered by the transmission line. Okay, done. So next, let's look some problems in this capacitance calculation. So I'm taking up the first problem here. Just look. First one. Consider the following three-phase system. Consider the following three-phase system. Just look here. So it's a phase A, phase B, phase C, phase A, phase B, phase C. Yes, is that spacing? This distance is 8 meters. This distance is 10 meters. Let's say, then yes, I'll say it is 40 centimeters. So, diameter of each subconductor is conductor is 4 centimeters. Diameter of each subconductor is 4 centimeters. The length of transmission line is line is 180 kilometers. Length of transmission line is 180 kilometers. The value of line charging reactance. Line charging reactance is dash kilo ohms. Line charging reactance is dash kilo ohms. Why it is shunt element? I have discussed long back, no Shiva? Discussed long back. Just recall thing what we have discussed earlier. We have discussed that in the basic elements placement only. Yeah, okay. Try to do this problem quickly. See what is asking as a final requirement. That's concentrate first. Later on, we will look into that each and every point. Value of line charging reactance is asking. What is the line charging reactance? That is nothing but shunt capacitive reactance. Line charging reactance is nothing but the shunt capacitive reactance, XC, per phase. Of course, if it is a three-phase system, we should give the value in terms of per phase only. Okay. So per phase. What's the formula for this one? 1 by 2 pi f into C per phase. Okay. So anything mentioned about frequency in the problem? Anything mentioned about frequency in the problem? No. So you consider that as 50 Hz. You consider that frequency as 50 Hz. Okay. Now, what is capacitance per phase formula? What is the formula for the capacitance per phase? Whatever it is, either it is a three-phase system or single-phase system, bundle conductor, whatever it is. Formula will start with 2 pi epsilon naught epsilon r in the numerator by natural logarithm. I'll say GMD in the numerator. Okay. Denominator, I'll keep it as ds. I'll keep that as ds as a notation. dsc also you say dsc. Okay. A ds cap better. ds cap capacitance. ds capacitance. It will be in farad by meter. That units is very important because he is asking us to find for total length. For the total length. Okay. What is GMD? It's a bundle conductor system. Bundle conductor system. What is GMD? A to B distance, B to C distance, C to A distance, geometric mean we should consider. Okay. So let's say GMD here, nothing but cube root AB, BC, CA. So it will come cube root AB 8, BC 10, CA 18 meters. How much is this? Tell me anybody. What is this GMD value? 11.29 meters. Good. 11.29 meters. Okay. What is DS here? As it is a bundle conductor, the DS calculation will be similar to GMR calculation. We said DS calculation will be similar to GMR calculation. And you should say DS of phase A, DS of phase B, DS of phase C, geometric mean. DS of the phase A, DS of the phase B, DS of the phase C, geometric mean. And all the three bundle conductors are identical. Phase A, phase B, phase C, bundle conductors are identical. So you can call this simply DS of phase A. What do you mean by DS of phase A? I have two conductors with diameter of each subconductor as 4 centimeters. So radius will be 2 centimeters. Spacing is 40 centimeters. Spacing is how much? 40 centimeters. So this will be resulting into a term like root of R into S. R into S. All of you getting this equation? Yesterday also we discussed about this one. Root of R into S. And radius is 2 centimeters. Spacing is 40. Radius is 2 centimeters. Spacing is 40. Okay. So how many centimeters you will get this one? DS cap. It will be 8.944 centimeters. 8.944 centimeters. And you keep this in meters for easy substitution. So it will be 0.08944 meters. 0.08944 meters. Okay, that you substitute and you find out capacitance in per meter. Capacitance per phase per meter. 2 pi epsilon naught. 8.854 into 10 power minus 12. Epsilon r 1 by natural logarithm GMD by DS. GMD number 11.29 and DS cap 0.08944. And it's in farad by meters. Okay, you please get this number. How much capacitance? So it is 2 pi epsilon naught by natural logarithm of 11.29 by 0.08944. It will come like 1.149 or 11.5 into 10 power minus 12 farad by meters. 11.5 into 10 power minus 12 farad by meters. Farad by meters. Let me write this like 11.5 into 10 power minus 9. 10 power minus 9. 10 power minus 3 we will take to denominator. 10 power minus 3 we will take to denominator. You call this farad by kilometers. 10 power minus 3 take to the denominator. It will come to be farad by kilometers. How many kilometers we have? The length of line 180. 180. Multiply that 180 so that we get the capacitance for total length of line. Capacitance for total length of line. For a length of 180 kilometers, capacitance per phase will be 11.5 into 10 power minus 9 farad by kilometers into 180 kilometers. So kilometer will be cancelled out. Kilometers will be cancelled out. So 11.5 into 10 power minus 9 into 180. So 2.07 into 10 power minus 6 farads. 2.07 into 10 power minus 6 farads. That you substitute in the XC. So for total length, I am saying directly. Total length. XC per phase formula, value 1 by 2 pi. 50 hertz is the frequency. Capacitance value 2.07 into 10 power minus 6. You have to give this number in kilo ohms. 1.537 kilo ohms. What is saying this 1.537? Are you getting this number? Getting this? Please check. 1 by 2 pi f into 2.07 micro. 1.538 or 1.537. Let's say 8 kilos. So the answer what we have to keep in the blank is 1.538. That's it. Already he said in kilo ohms, right? Already he said in kilo ohms. So you should keep this number 1.538. That's it. Okay. So your answer will be 1.538. Done? Yeah, right. So next, let's take one more problem in this capacitance calculation quickly. One more problem. Going to next slide. So it's a question from our classroom practice questions. Just check this. Go through it. Go through this one. Already, I have uploaded that file in that portal. Please download it and take it as a printout so that you no need to write the question. Just you can write that question number and you can proceed with this. Read this one. A three-phase equilateral spacing conductor system with 6 meters spacing between any conductors operated at 132 kV, 50 Hz. The diameter of each conductor is 0.04 meters. If the system is operated for balanced voltages, the interline capacitance of the system is dash nanofarad by kilometers. See, if you look into this question properly, what you can understand is we have an equilateral spacing system. That's one statement what he said as a first line. So let me show that equilateral spacing system. So this is a phase A conductor, and phase B conductor is also of the same size. Phase B conductor is also of the same size, and phase C conductor is also of the same size. Okay, so these are the conductors A, B, C. Next, 6 meters spacing between the conductors means A to B, 6 meters. B to C also 6 meters, you can say. C to A also 6 meters. Done. Next. Diameter of each conductor is 0.04 in the sense radius of each wire is 0.02 meters. Very simple question it is. Conductors are operating for balanced voltage. That's well and good. The interline capacitance of the system is dash. Interline capacitance means what? What do you mean by interline capacitance? Line to line. Conductor to conductor capacitance he is asking. Okay. So, first of all, if I repeat this diagram, I'll repeat this diagram in the next slide. Look this one. Yeah. So these are A, B, C conductors. ABC conductors, right? And the interline capacitance means conductor to conductor capacitance. You can show simply like this. A to B, B to C, C to E. These capacitances we need. Of course, all the three capacitances will be equal. All these three capacitances will be equal. Just look at this question, what I am asking you. Look at this question. What is formula for the CAV? What will be the formula for the CAV? Anybody? What will be the formula for CAV? It's not with pi. It's not with pi epsilon naught epsilon r and all. Pi epsilon naught epsilon r by ln of d by r is valid for only single phase two wire system. This formula is valid only for single phase two wire system, not for three phase. Okay, so as far as three phase is concerned, you know capacitance from A to neutral, B to neutral, C to neutral, na? That we will try to use in order to get the line to line capacitance. Okay, so let me show the same diagram here. I am showing the same diagram, means same conductors configuration, same conductors configuration like this, and I will show here conductor A to neutral capacitance, conductor C to neutral capacitance, conductor B to neutral capacitance. Okay. Next thing. What is it CAN formula? What is it capacitance from conductor A to neutral formula? CAN formula already we have 2 pi epsilon naught epsilon r by natural logarithm GMD by R. Farad by meter. That is CAN. What is the relationship between the CAN and CBN? From the star to delta conversion. From Y to delta conversion. Delta conversion. This you might be studying in network theory. By using that conversion, capacitance CAB will come to be CAN by 3. Capacitance CAB will come to be 1/3 the value of CAN. Okay. Fine. Let's continue with the CAN calculation. After that, I will take 1/3 to get the value of CAB. What is GMD? First, what is GMD? It is cube root of DAB, DBC, DCA. Cube root of DAB, DBC, DCA. So it is 6 into 6 into 6. Come to be 6 meters. Already R we have, that we will dump into the equation, we will get CA. So capacitance from conductor A to neutral will be 2 pi epsilon naught. Epsilon R is 1 by natural logarithm GMD by GMR. Farad by meter. Yeah, you please get this number. Please get this number. How much? 9.75. Approximately 9.75 into 10 power minus 12 farad by meter. 9.75 into 10 power minus 12 farad by meters. Okay. So, but he is asking that answer in nanofarad by kilometer. Nanofarad by kilometers. I'll say first 9.75 into 10 power minus 9. The 10 power minus 3, I will take to the denominator. It will come to be farad by kilo. 10 power minus 9 is nano. So it will be 9.75 nanofarad by kilometers. Nanofarad by kilometers. Okay. Now, therefore, interline capacitance CAB will be equal to CAN by 3. What you get now? 3.25. Come to be 3.25 nanofarad by kilometers. So the value what we have to type in the blank, is 3.25. You have to type 3.25 in the blank. 3.25 nanofarad by kilometers. Okay. Let's take a small conclusion now. Let's take a very small conclusion. What is capacitance per phase? In the previous problem, per kilometer capacitance. In the previous problem, already I have moved to previous problem. What is the capacitance per phase here? It is like 11.5 nanofarad by kilometer. Are you getting this? What I'm saying? In the previous problem, capacitance per phase value 11.5 nanofarad by kilometer. In the present problem, how much is this capacitance per phase? C per phase value, you are getting like 9.75 nanofarad by kilometer. What's the conclusion now? Both values are looking almost same. Yes or no? In the previous problem, done the capacitance calculation with some numbers. You got 11.7. Now you are doing with some other numbers. You are getting that value 9.7. Both numbers are a bit close on. See, my intention is again to tell you this formula will be remain same. Whether it is a 130 kV line, 400 kV line, 75 kV line, this formula will be remain same now. So formula remains same. Only the change in the capacitance value will come because of the change in GMD by R. Because of that, as it is inside the natural logarithm, the variation we may not expect as a great. So that for any single circuit 3-phase transmission line, single circuit lines, capacitance per phase or capacitance per conductor will be around 10 nanofarad by kilometer. 10. Sometimes more than 10, 11 it may come. Sometimes less than 10, maybe 9 9.8, 9.7, like that also we can experience. Okay, so in general, so you can say it's a note. In general, the capacitance per phase of a single circuit transmission line will be around 10 nanofarad by kilometers. 10 nanofarad by kilometers. All of you getting it? 10 nanofarad by kilometers. So I am asking one very simple question. Simple question. Just try to answer this one. A three-phase 66 kV line has inductance and capacitance. Capacitance per phase values as option A, L equal to per phase has inductance and capacitance per phase per kilometer values as look, first L 0.1 millihenry, C 9.8 nanofarad, option B L 1 millihenry, C 9.8 nanofarads, C L 2 millihenries, C 9.8 microfarads, D L value 0.01 millihenries, C 9.8 microfarads. Which will be the suitable option? Which will be the suitable option? See, sometimes in what we call examinations, you can observe a question of this kind, and many people will say that it's a improper data. They have not given any radius of conductors, distance between the conductors to calculate the values of inductance and capacitance. How I can say inductance value and capacitance value of that line? We have to go with a what we call approximation. We know already inductance per phase will be in the range of 1 millihenry per kilometer to 1.2 millihenry per kilometer. Which value will fall in that category? Option B, 1 millihenry. Okay. How is the capacitance value? It will be in and around 10 nanofarad by kilometer. And for the same option, they have given 9.8 nanofarad. It's a suitable number to be chosen. So correct answer will be B. Correct answer will be B. All of you getting it? Yeah. So next, let's continue with this. So till now, we have done the calculations of RLC parameters. From now onwards, I want to check what will happen to these values with physical parameters variation. With the physical parameters variation, what will happen to these values? Maybe if I say length of line is increasing, what will happen? If radius of conductors are increasing, what will happen? Distance between conductors are increasing, what will happen? Okay, right. So variations in the parameters with respect to physical parameters. Let's take a small table here. So I'm saying first here parameter. Okay. And RLC, I am calling the resistance, inductance, capacitance. Next, inductive reactance, what will happen? Capacitive reactance, what will happen? Charging current, what will happen? Let me discuss about these three also, remaining three also. Okay? Yeah. So let's say resistance variation, we should say increasing, decreasing, or constant. That's a thing. Capacitance, increasing, decreasing, or constant. And similarly, XL, and it's XC, and it is IC, charging. Okay? Yeah. So I'll say first parameter. First, with respect to length of line, what will happen? First one is length of line is increasing. Length of line is increasing. What will happen to resistance value, inductance value, and capacitance value? Tell me, please. Inductance is in the what range? Yesterday we discussed, no, Raj. Just you go through the previous class notes. I have discussed about that inductance. Yeah. Listen. What will happen to RLC with respect to increment in the length of line? With respect to increment in the length of line, resistance value definitely increases. Resistance value definitely increases. What will happen to inductance? Inductance increases. Capacitance value, what will happen? Capacitance value, what will happen? That's also increases. Capacitance value also increases with respect to increment in the length of line. Very simple. Resistance is a series element. Resistance is a series element. So if length of line is increasing, some more resistance will add in series. Resistance is increasing. Inductance, series element. If some more inductance is added in series, overall inductance will increase. Capacitance is a shunt element. Okay. But if you are adding some more capacitance in parallel, overall capacitance will increase only. Na? If length is increasing, some more capacitance will come in parallel, right? So overall capacitance value also increases. What will happen to XL? What will happen to XL value? XL. See, this inductive reactance XL is proportional to inductance. Proportional to inductance, where you know inductance is proportional to length. Length increasing, inductance increases, XL value increases. What will happen to XC? XC proportional to 1 by capacitance. XC proportional to 1 by capacitance, and capacitance is proportional to length. Capacitance is proportional to length. So if length is increasing, capacitance is increasing, and XC value will fall down. XC value will fall down. And what about charging current IC? Tell me please. What about charging current IC? IC, already we mentioned that it is proportional to voltage into frequency into capacitance. Na? Length increasing, capacitance will increase, charging current also increases. Charging current also increases. So these are the variations in RLC, XLXC, and charging current we can find with respect to increment in the length of line. Respect to increment in the length of line. Next one. Radius of the conductors increasing. Size of the conductor is increasing. Radius of conductors increases. See, if radius of conductors are increasing, definitely GMR value will increase. Na? Definitely the value of GMR increases. Radius of conductors increasing means GMR value will increase. Okay, what will happen to resistance? What will happen to resistance? If radius is increasing, area of cross section is more, resistance value will decrease. Resistance value will decrease. Inductance, what will happen to inductance? You know, L proportional to, please stop writing. Please stop writing and listen. L proportional to natural logarithm of GMD by GMR. Natural logarithm of GMD by GMR. We should not write inductance proportional to ln of 1 by GMR, or inductance is proportional to natural logarithm of GMD. This type of things we should avoid. We should not write in this manner. It's completely wrong. Completely wrong. We should not write like this. Even though one of these two is constant. GMD is constant now. We are saying only GMR is varying. But still you should write ln of GMD by GMR. I should not push this GMD into proportionality constant. I should not move this GMD into proportionality constant. Kindly listen to this. Okay. We should write always inductance is proportional to ln of GMD by GMR only. Okay. So now if GMR is increasing because of increment in the size of conductor, GMD by GMR will decrease. So inductance value will be decreasing now. Inductance value will be decreasing now. So I can say L value decreases. L value decreases. Similarly, capacitance if you talk. Similarly, if you talk about the capacitance, C proportional to 1 by natural logarithm GMD by radius. Okay. So 1 by natural logarithm GMD by radius. And you know, if radius is increasing, GMD by R will decrease. Capacitance value will increase. Capacitance value will increase. So capacitance value increasing. Okay. What will happen to XL? XL proportional to inductance. XL proportional to inductance. Inductance is decreasing. XL decreases. XC inversely proportional to capacitance. Capacitance is increasing. XC value decreases. Right? XC value decreases. And charging current? Charging current. Charging current proportional to capacitance value. Capacitance is more. Charging current is also more. Capacitance is more means charging current is also more. Clear? Next thing. Distance between the conductors are increasing. Distance between conductors increasing. See, whenever distance between conductors is increasing, obviously I can say GMD value will go high. GMD value will be increased. Tell me now, because of that increment in the GMD, what will happen to resistance? What will happen to resistance? No change. No change in the resistance. XC proportional to capacitance, Bhavana. Inversely proportional to capacitance. Already we have written here, right? XC inversely proportional to capacitance value. And you know this capacitance is increasing and reactance will decrease. Okay, look at this. GMD. No change in the resistance. No change in the value of resistance. Yeah, next thing. What will happen to L? Inductance. You observe. GMD increasing means L will be increasing. L will be increasing. Inductance increases. Capacitance. GMD increasing, na? Denominator will increase. Capacitance will decrease. Capacitance will decrease. XL proportional to inductance. Inductance increasing means XL increases. XC inversely proportional to capacitance. Capacitance decreasing means XC will increase. Charging current is proportional to capacitance number. Charging current is proportional to capacitance. Yes. See, when we are capable to make these variations in the length, radius, and distance, when we are capable to make these variations in the length, radius, and distance, at what stage? At what stage? Is it at designing or operating? Only at the designing stage you can make these variations. Okay, once after design is completed, constructed the line. constructed the line on the towers, then you don't have any chance. You don't have any chance of varying length, radius, and distance between the conductors during operation, you can say. Okay. So all this discussion we are doing at design stage. Designing stage. Now let's call during operation now. During operation. During operation. Tell me please. During operation. During operation. For example, I'll say frequency of operation was increasing. What will happen? See, again, during operation also frequency is increasing means it won't shoot up from 50 Hz to 60. It won't happen like that. Small change. Maybe 50 increase to 50.1, 50 decrease to 49.9. Like that, we have a change. But still, as a study or for the examination purpose, if I say frequency of operation was increased, what will happen? Frequency of operation was increased. I'll keep this as a heading. That may be better. Okay. If frequency of operation increases, number one, you say this. That frequency of operation was increased. What will happen to resistance? What will happen to the value of resistance? Almost constant by neglecting skin effect. By neglecting skin effect, resistance is almost constant. Resistance will be almost constant. Okay, what will happen to inductance and capacitance? What will happen to inductance and capacitance values? Will these values depend upon frequency or not? This is a place where you should have a better clarity. Try to answer it properly. Inductance value and capacitance value depends upon the frequency of operation or not. No. Where is that inductance? Sir, where is that frequency in inductance formula? What is formula of inductance? 0.2 ln of GMD by GMR. Where is that frequency term? What is capacitance formula? 2 pi epsilon naught epsilon r by ln of GMD by R. Where is that frequency formula? Frequency term. So L and C values, of course, R also are independent on the frequency variations. I think you are clear. No change. No change in L and C values. But XL, XC will change. Inductive reactance will change. Capacitive reactance also changes. But I don't have any change in the values of L and C. See, simply this RLC parameters, what we are talking now, RLC parameters depends upon dimensions of the system. Dimensions of the system in the sense, size of the conductors, spacing between the conductors, conductor type, what type of conductor you are using, and material what you are using. These things, physical parameters will decide the values of RLC numbers. Okay. But you know, XL and XC, XL proportional to frequency, so increases. XC inversely proportional to frequency, XC decreases. Charging current proportional to frequency, so charging current will increase. Frequency increasing means charging current will increase. Already I have given the relationship. IC proportional to voltage into frequency into capacitance. Frequency increasing means charging current will also increase. Okay, next thing. If operating voltage increases, what will happen? Next one is, if operating voltage increases. This is our question actually, right? If operating voltage is increasing, we should investigate what will happen to RLC, XLXC, and then charging. Yeah, Vishnu, what I am saying is, even though we have a change in the frequency, change in the frequency, change in the resistance is neglected. Change in the skin effect is neglected. That's a meaning there. But of course, you know, skin effect definitely depends upon the frequency, but frequency variation is very less now. So skin effect variation is very less. So resistance variation is also a bit less. So that we are assuming that is constant. Yeah, you please tell me what will happen to resistance value after the voltage, operating voltage was increased. What happens to resistance? Resistance, what will happen? No change. Yeah. No change in the resistance value. What will happen to inductance? No change. Capacitance? No change. XL? No change. XL depends only on frequency. XC? No change. Charging current? Charging current. Charging current depends upon the voltage. Charging current depends upon the voltage. See, these 5 numbers are constants. Constant. Okay. But you know, charging current is proportional to voltage. Voltage is increasing means charging current will increase. Voltage is increasing means charging current will increase. So these are the variations in the parameters with respect to frequency and voltage during operation. During operation. So I will be stopping the session at this point. At this point itself, I am stopping the session. Tomorrow again we have a class from 6:30 to 9:30. 6:30 to 9:30. Tomorrow we'll take up to 9:30 definitely. So if you have any doubts, you can ask me now. If you have any doubts, you can raise your hands. I will make all the hands low. All hands low. Okay, you can raise your hands, please. Ramakrishna.
Yeah, hello, good morning, sir.
Good morning, Ramakrishna. Tell me.
Sir, these capacitance values are much small now, so will they make any large changes in the system parameters of voltage?
Definitely, it will change. It will change. Charging current will change.
General transmission line of receiving end and
See, if the length of
sending
line
end.
is very high, definitely it's going to show a large effect, right?
Yes, sir. Yes, sir.
For
Okay.
short length of lines, it may not show a great effect, as you said.
Okay, okay. For long transmission lines,
Long lines and medium lengths of lines, definitely it will show the effect.
Okay. Thank you.
Okay.
Yes, sir. Okay.
Yeah. Any other doubt you have, Ramakrishna?
No, sir. No, sir. Yes, sir.
One more thing, Ramakrishna.
Yes, sir.
How can you say that capacitance is low?
Generally, in where the problems we do, we take microfarad, no, sir. These are in nanofarads and per kilometer also. So
1 minute. Don't feel about my explanation.
Yes,
what I am making.
yes, sir.
Okay. Just jovially I am talking with you.
Yes, sir. Yes, sir.
Where you have seen that capacitance microfarad?
Generally, in lab also we make, no, sir. Lab.
In electronic circuits.
Yes, sir.
How can you compare that capacitance
Power
with this,
okay.
Ramakrishna?
Yes, sir. Okay.
Yes or no?
Yes, sir. Yes, sir. Okay, sir.
That type of comparison you should not make. Within the same system, we should compare.
Okay, okay, sir.
Best comparison, what I will tell you is XL XC comparison.
Okay, sir.
And you can make a comment now. XL will come very low, sir. XC will come very high. That's why as XC is very large in number, because we calculated some problem. Kilo ohm you got. But how many kilometers? 180 kilometers only you got kilo ohm.
Yes, sir. So
1 kilometer you take, it will come in mega ohm.
Sir.
Okay.
Okay.
So in that perspective, the shunt current may be very less. But if length of line is very high, shunt current is appreciable with respect to load current.
Okay, sir. Okay.
Then we have to take it into circuit.
Okay.
Okay, just by looking at the number, I can't decide is it low or high if I don't have other number to me.
Yes, sir. Yes, sir.
Yeah. Okay.
Okay, sir. Thank you.
Yeah. Fine. Bala Vinkesh. Bala Viknesh. Sorry. Bala Viknesh. Bala Viknesh, do you have any doubt? Bala Viknesh.
Sir,
Tell me, Bala Viknesh.
sir, 132, sir.
Okay.
Sir, here, what is the difference between GMR and DS cap, sir?
Only that 0.7788 is missing. That's only the thing I said.
Okay, sir.
Because you don't have any internal electric flux linkages.
Okay, sir. Sir, in bundle conductors, GMR also means R dash is equal to 0.7788 into R, no, sir? For
In case
bundle
of
conductor.
inductance calculation,
Okay, sir.
not in capacitance. In inductance calculation, you should take R dash into S.
Okay, sir.
Okay.
Yeah, that's it, sir. Thank you, sir.
Pranjali.
Hello, sir.
Tell me, Pranjali.
Sir, slide 122.
Okay.
Sir, here, you have represented V2 and V3. Sir, if we like mark that at equal distance from the center, then sir, can we say that value of V2 and V3 will be same?
Actually, you see, one side positive, one side negative, you may get, right, Pranjali?
Yes, sir. Yes, sir.
Then also both are unequal.
Yeah, sir, means sign different but magnitude same.
Whatever it is, V2 is not equals to V3. That's it.
Yes. Okay, sir.
Magnitudes are equal, but there is a sign difference, as you said.
Yes,
Unequal
sir.
voltage. Na?
Okay. Yes, sir.
Yeah.
Okay. Thank you, sir. That's
Yeah.
it.
Okay. Shay.
Sir, can you hear me, sir?
Yeah. Please tell me.
Sir, I wanted to know the difference between line charging current and charging current.
Both are same names. Don't differentiate them.
Like everywhere it will be same, or in our case,
Everywhere it will be same. Line charging current or charging current simply both will be same. Per phase charging current.
Okay, so sir, the doubt came because in the diagram you mark the current in the phase one current and the other one in the current going through the capacitor. So
Current going through the capacitor. Where?
yeah, here I see per
This
phase.
one?
Yeah, correct.
Okay, this current and this current both are same, right? That current is flowing in the capacitor only.
Yeah, in this case it will be same. Like I was just wondering if in some other case it would differ. So
No. It won't differ, I think, Akshay.
okay, sir.
Where you got the difference? You show me in a diagram, I'll tell you.
Okay, sir.
Okay?
Okay. Thank you, sir.
Nagavishnu.
Sir, good morning, sir.
Good morning, Vishnu. Tell me.
Sir, here in inductor, it's a designing stage. When length is increased, you said that inductance will also increase, no, sir?
Yeah.
But coming to the basic physical property formula of inductor, length is inversely proportional. Inductance is inversely proportional to length, no, sir?
What is it? A basic formula of inductance?
L equal to mu n square A by L, no, sir?
What is that L?
Length of that inductor, no, sir? That
Length of
coil.
flux linking path.
Sir?
L is a length of flux linking path.
It is not it.
It's not length of
physical.
coil.
Okay.
If this is a coil, you will have the flux linking path something like this. Okay?
Yes, sir. Yes, sir.
That is that length, this length. Else, listen.
Yes, sir.
It's a core, magnetic core.
Yes, sir.
Okay, so I am keeping one coil here on this. Okay. Now, if you want to take that formula for this coil, L is equals to mu n square A by L.
Yes, sir.
What is mu? Mu equals to mu naught into mu r. Permeability. That mu r is for this material you should take. N
Yes,
number of turns. A, area of cross section of coil or area of cross section of core also.
Yes, sir.
What is L? That is this L, right?
Okay, okay, sir.
This is a path through which that flux is linking. This total length, for example, you say this height, mean height you should take, strictly speaking, take some value. It is some 2 meters, it is some 2 meters, it is some 1 meter, it's some 1 meter. Then L will come approximately, it will come to be 2 plus 2, 4 plus 1, 5 plus 1.
6.
That's it.
Okay, okay, sir.
Understood?
Yes, sir. Yes, sir.
Yeah.
Thank you, sir.
Then how that L is related with our conductor system? GMD.
Okay.
Okay?
Yes, sir. Okay, sir.
Yeah. Any other doubt you have?
No, sir. No, sir. That's
Same.
Yes, sir. Good morning, sir.
Good morning, Same. Tell me.
Sir, I am audible. Yes. Okay.
Yeah.
Sir, in that conductive plane, effect of earth in the capacitance. Okay. It is a infinite surface, so it is a infinite conducting plane. So for the upper part, Q and minus Q, then total electric field will be 0 inside that.
Inside means where?
Means
Inside.
for that infinite plane, it is like a infinite surface, and there is a confined plus Q and minus Q is inside that surface.
What law you are applying there?
That is Gauss law.
Gauss law.
Okay. If I am putting a charge in a small radius, and it is a conducting plane, and the outermost is grounded.
See, actually, Gauss law, what it is going to tell for you is, if you have a closed surface,
yes,
or closed area, whatever it is, and net flux coming out from that is a charge enclosed.
yes,
Yes or no?
yes.
For example, if you close this plus Q and minus Q together, what is the net flux coming out?
Net 0.
0. But you have a flux line in this direction, flux line in this direction.
Yes.
He's saying that both are cancelling and net is 0.
Okay.
But does not mean that here we don't have flux. Nah? Here we have a flux, right?
But we experience outside that surface no electric field.
No. See, what Gauss law says is net flux coming out is 0.
Yes.
Total flux coming out, total flux coming out is equals to charge enclosed.
Yes.
Okay, but not at each and every point, nah?
Yes, sir. Yes.
At each and every point, you might be having a flux, but if you sum up all the things, that will be equals to charge enclosed.
But if we go inside that, is there we will experience any?
See, actually, Swain, at all the places you have a flux, Swain. At all the places you have a flux here.
Yes.
But sum of all these things will be 0, because sum of these two charges equals to 0. Because one is in one direction, other one is in opposite direction.
Okay. If sir, I will remove one charge, that is minus Q charge.
If you remove it, then obviously all the flux are going out, all the flux lines are going out.
Yes.
Then obviously the total will be outgoing only, outgoing. That will be equals to Q, what he's saying.
And if that conducting plane is grounded, let's suppose, that is at a 0 potential.
Which one? Q?
That Q is inside a material which is grounded, that is circular area.
Okay.
Then what happen actually? Charge will
then obviously net flux is leaving out only, nah?
But we studied in minus Q charge.
Actually, listen, Swain. Ground is assumed as 0 potential plane after this explanation.
Yes.
Not before this.
Yes.
We are keeping a charge inside the ground. Okay. And obviously, with effect of the charge, Earth is as a whole is going to act as a charge only, na?
So it is not understood.
No, you are keeping charge inside the ground.
Yes.
With effect of that, it will be acting as charge only.
Yes.
Then obviously it will be leaving the flux lines or taking the flux lines. Anything may happen. That depends upon the plus Q and minus Q nature.
Yes.
That's it. That's what I'm saying.
It may be a infinite conducting plane, or it may be a ground also.
Anything.
Okay. And if it is grounded, then is negative charge is induced on the surface of that conducting plane? Like we studied that plus Q and minus Q will be induced in capacitor. Like
one thing. If you want to understand in another way, I'll tell one more thing is also there. It is plus Q charge.
Yes.
It's a ground.
Yes.
I don't have anything beside this plus Q charge, only ground. See, this plus Q charge is leaving the electric flux lines like this.
Yes, sir.
Where these electric flux lines should go?
The some will be passed to the conducting plane, some will be leaving upward.
Upward, okay. Whatever it is touching this conducting plane should be terminated at some point, right? Definitely.
Yes.
At some negative charge. That charge we are assuming as minus Q.
Okay.
Below the ground.
Yes, sir. Yes. Now.
Okay.
Yes, sir. Thank you. Thank you.
Avinash.
Hello, sir.
Tell me, Avinash.
Sir, 115. 115, sir. Slide number
115. Okay. Yeah.
Sir, 115, sir. 15.
115.
Yes, sir. Yes, sir. Yeah, 115. Right, sir. Yeah. Sir, in this we have taken a d in a logarithmic term. D is here and r is here. So how it will be, sir?
Oh, ln of 1 by r minus ln of 1 by d.
Yes, sir. Yes, sir. So at both places there should be d or there should be r, sir. Then how we can take?
No, I didn't get you. Please elaborate what you are asking exactly.
Sir, in the first term we have take a natural log of 1 by r, and in the second term we have take natural log of 1 by d.
Okay.
So sir, how we can
We have
take
minus sign here.
Different. Yes, sir. Minus sign here, but sir.
After applying minus sign, ln of 1 by r minus ln of 1 by d.
Yes, sir. Yes, sir.
That minus, if you push into natural logarithm, it will come ln of d.
No, sir. That's not point, sir. Sir, here we have taken r and here we have taken d, sir. So means why we have taken different, sir?
See,
means at both places we have why we.
This is voltage on the conductor A due to its own.
Yes, sir.
This is voltage on the conductor A due to B.
Yes, sir.
Superposition principle.
Okay, sir.
If you want to find out voltage at one point, you should take up the effect of all other charges beside to that, right?
Yes, sir.
Yeah.
That means if for its self EMF, sir, then we have taken R and
that EMF is different phenomena. Why you are talking about EMF here, Avinash?
Yes, sir. Yes, sir.
It's a electric flux phenomena we are talking, not EMF.
Okay, sir. Sir, actually, I have not got, sir, this equation. Please, we can
see. This is due to its own conductor. Okay.
Yes, sir.
And this is due to conductor B beside to this. Beside to that. Now you tell me what's your doubt.
Sir, in the due to its own conductor, we have taken it R, and due to its
because this is a radius. Already I have explained about this.
Okay, sir.
This one. Beside to a conductor at a point x, sir, it will be q by 2 pi epsilon into ln of 1 by x.
Yes, sir.
On the surface itself, it will be x replaced with r.
Yes, sir.
So on the conductor itself, you are interested to know first. On the conductor itself means q by 2 pi epsilon into ln of 1 by r.
Yes, sir.
Due to the other conductor B, it will be minus q by 2 pi epsilon ln of 1 by how much is the distance from B to A? D. Because this is a point where you are calculating voltage, right?
Yes, sir. Yes. Right.
So at this point, you are calculating. So because of its own conductor, you will get only radius.
Okay, sir.
Because of the other conductor, you will get the distance between that
Yes,
other
sir.
charge and the point where you are staying.
Yes, sir. Now got it.
Clear?
Yes, sir. Clear. Thank you, sir.
So, Pratyusha,
Sir,
tell me.
in slide number 138,
Okay.
once explain that problem, sir.
I explained already. Capacitance, are you clear?
Yes, sir.
Okay. Inductance, have you attended previous classes?
Yes, sir.
I discussed at one point inductance value by the same meaning of GMD by GMR variation. It won't have a great value variation. It will be coming in the range of 1 to 1.2 millihenry by kilometer as a conclusion.
Okay, sir.
Similar to capacitance, inductance value will be having some range.
Yes, sir.
Per kilometer. That will be in the range of 1 to 1. Just check back.
Okay, sir.
I think at some place I'll show you if possible. Here I have discussed. You check once. This one.
Okay, sir.
Hmm?
Okay, sir.
Yeah.
Sir, in slide number 136, why we consider that CAV equal to CAN by 3?
From star to delta conversion. You might have studied this in networks. The networks from star to delta conversion, the delta capacitance will be 1/3 of the star capacitance.
Okay, sir. Sir, if distance between conductors increases, why the inductance value is increasing and capacitance value is decreasing?
Formula. Go through the formula. This formula. Distance is increasing, GMD will increase. So inductance will increase.
Okay, sir.
GMD is increasing, denominator is increasing, capacitance will decrease.
Okay, sir.
Okay.
Sir,
So any other doubt you have?
Another doubt, sir.
Tell me.
Capacitance with earth effect in that we have write that from 2h by square root of 2h whole square plus d square, na, sir.
Okay.
A value ఎలా వచ్చింది, sir?
That's a derivation.
Okay, sir. Once explain last slide.
Which one? Number 130?
Last slide, sir, in today's class.
Okay. What's the doubt you have in that?
Not that, sir. During operation.
Tell me.
Once explain second point, sir.
This one, operating voltage.
Yes, sir.
See, RLC parameters depends upon only dimensions of system.
Okay, sir.
Even though the voltage is varying, dimensions of system will not change, na?
Yes, sir.
So RLC will be remains constant.
Okay, sir.
XL value formula 2 pi f into inductance.
Yes, sir.
There is no voltage term in that.
Yes, sir.
XL is also constant.
Okay, sir.
XC 1 by 2 pi f into capacitance.
Yes, sir. No voltage.
So there also no voltage term. So XC also constant.
Yes, sir.
Okay.
Yes, sir.
Yeah. So any other doubts you have?
Sir, in that you have wrote IC is directly proportional to V.
That also we have discussed in the formula, I think so. This one. V phase by XC per phase.
Okay, sir.
V phase into 2 pi FC per phase. Okay.
Okay, sir. Thank you, sir.
Yeah. Imtiaz.
Good morning, sir.
Good morning. Tell me, Imtiaz.
Sir, could you explain what is the line charge current, sir?
Line charging current is nothing but current flowing in the line because of electric flux. That's it.
Okay, I thought any difference in the capacitance and line charge.
No, not because of that. It is dq by dt.
Okay, sir. Sir, we are discussing that ES is equal to R into S, but we are not considering the 0.77 because of the inside we not considering the
Yes,
uh,
flux,
skin
electric
effects.
flux. Electric flux is not there inside.
Oh, okay, okay. That's all, sir.
That's it.
Thank you, sir. Hi, sir. Thank you.
Any more doubts? You can raise your hands. Ajay,
Good morning, sir.
good morning, Ajay. Tell me.
Sir, last slide, sir.
Last slide.
Operating voltage.
Tell me, what's the doubt you have?
సార్ మనం అంటే ఇక్కడ ఆర్ఎల్సి అనే ఆపరేటింగ్ వోల్టేజ్ ఇంక్రీజ్ అయిన ఆర్ ఈక్వల్ టు మనం V/I అని రాసుకున్నాం కదా, ఇక్కడ ఏంటి కన్సిడర్ చేసుకుంటాం సార్?
ఏంటండి?
ఆర్ ఈక్వల్ టు V/I అని అనుకుంటాం కదా సార్ మనం రెసిస్టెన్స్ ఎస్ సార్. ఇప్పుడు
రెసిస్టెన్స్ ఫార్ములా ఏంటి?
అంటే V/I అని రాసుకుంటాం, రోయల్ బై ఏ అని.
ఏ ఫార్ములా కరెక్ట్ ఆ రెండిట్లో?
రోయల్ బై ఏ.
మరి ఇంకా అది వోల్టేజ్ మీద ఎందుకు డిపెండ్ అవుతుంది? మీరు అప్లై చేసిన వోల్టేజ్ బట్టి కరెంట్ ఫ్లో అవుతుంది.
ఎస్ సార్.
ఓకేనా?
ఎస్.
రెసిస్టెన్స్ వాల్యూ నీకు వోల్టేజ్ కరెంట్ చేంజ్ చేస్తే రెసిస్టెన్స్ వాల్యూ చేంజ్ అయిపోద్దా?
కాదు.
Resistance value is independent on the operating voltage and frequency. Sir, operating voltage and current. R equals to V/I అనేది మీరు ప్రాబ్లం చేసేటప్పుడు రాస్తారు. ఓకేనా?
అవును సార్. అదే సార్, అంటే ఇక్కడ ఏంటి తీసుకుంటలేమని.
Resistance value is rho L by A that we are doing, which is independent on the operating voltage and currents. Okay, once after you know voltage and currents, based on that and resistance value, you can find out the remaining quantities whatever it is needed. అంతేగాని ప్రతి ప్రాబ్లం కి రెసిస్టెన్స్ వాల్యూ చేంజ్ చేసుకుంటూ పోం కదా.
ఎస్ సార్. ఓకే సార్, థ్యాంక్ యూ సార్.
ఓకే
ఓకే సార్.
ఓకే, సైన్ ఆన్.
Sir, how this epsilon naught and epsilon are actual in real time, sir? Meaning,
that's a property of mediums only.
Means is it conduction in air, sir?
Not conduction. Epsilon is a property of medium which will allow the flux flow, electric flux flow.
Is it resistance like that, sir, in the air resistance?
Equivalent to conductivity.
Conductivity in air.
No, conductivity of material.
Conductivity of material.
Conductivity of material. Relative permeability of the material, permittivity of the material. These are the three properties. Conductivity of the material shows its capability of allowing current.
Okay, sir.
Permeability of the material shows its capability of allowing magnetic flux.
Okay, sir.
Permittivity of the material shows the capability of allowing electric flux.
Okay, permittivity, electric flux, permeability,
magnetic flux.
Magnetic. And mu r and mu naught, sir. Mu r and mu naught.
Mu naught is a free space permeability. Mu r is characteristic of the material.
Sir.
Comparison. Just it's a comparison from one material to other material. For example,
Okay,
air is having mu r value 1.
Yes, sir.
Other material is having mu r value some 10.
Okay, sir. Yes.
Means what you should say, that other material is allowing the magnetic flux more properly as compared to air.
Air. Yes, sir.
That's the conclusion. Okay.
Okay, sir.
That's it, Saina?
Yes, sir. That's it.
Ramesh.
Sir, good morning, sir.
Tell me, Ramesh.
Sir, single phase two-phase system, we have not used two formula, capacitance formula, you not use two, sir. Like one second, answer that.
Single phase two-wire system.
Sir.
Okay, what's the doubt in that for you?
Hey, capacitance, we have not used a two-phase system. 2 pi formula, sir, in formula.
2 pi we have used,
We not used once.
2 pi only we have used, no? Where? What slide you have it out?
Sir. Sir, example voltage between A and B conductors, sir. Example taken practical example, single phase 2-phase.
Okay, tell me, what's the doubt you have?
Here 2 is not taken, sir. Why that?
Where?
Once explains. C
It's
phase C.
conductor to conductor capacitance.
Yes.
Already we have written CPN, phase to neutral. Between two conductors only, na capacitance value we are taking.
Sir.
Here also CAB if you write. Pi epsilon naught epsilon r by ln of d by r. Okay?
Okay, sir. Thank you, sir.
Yeah. Right. So I'm closing the session. I think nobody's having a doubt. Thank you.